held a postdoctoral fellowship at the Max Planck Institute of Light in Germany and the University of Strathclyde for 2 years in Scotland. So currently he held senior scientist at the Planck Institute for the Science of Light. And it's also notable to note that Dr. Hill has received numerous awards for his academic achievements, including the Professor John Parrott Prize from Cardiff University, the Fred Stern Prize from the University of Strathclyde, and recognition award at the 2021 UK Doctor Awards across all natural and life sciences. We are very excited to welcome you today to QuantLase Lab. Thank you for your time. And I would like to welcome Mr. Shiraz to the stage, just to welcome you. Thank you. And I hope you enjoy it.
Mic is not working that good. On behalf of QuantLase team, I would like to welcome Dr. Pramod.
So thank you very much, Dr. Hill. It's really a pleasure and privilege to have you today. And this meeting actually we were waiting for this event since last 4 years. So finally you accepted my invitation. Thank you very much. And about QuantLase, Lina already discussed everything and explained everything. So it's nothing new for me to further explain the things, and you already seen the lab. So regarding this today talk, because most of the people are not very quite familiar with this photonic community, and so I have humble request you to explain the things in a very layman language, then people get understand all these things. So your topic is is not usual topic, and breaking symmetry and the nonlinear dynamics. This is because ever increasing demand of transfer the technology in chip scale is a long-standing issue in the scientific community. So it's a dream to fabricate optical component on chip scale. But the problem is that when you fabricate all the component on chip scale, they interact each other and they create nonlinearity. In addition to all nonlinear optics, they create nonlinear dynamics. So this is the talk is merging between two phenomena: is symmetry breaking and nonlinear dynamics. So the bridge between nonlinear dynamics and symmetry breaking actually paving the way new technology, or it's another route or very specific route to do some things which is new regarding quantum computing, regarding quantum information, regarding imaging, sensing, and everything. Because this Kerr resonator is a specific resonator. There is a medium is intensity dependent refractive index. When you shine a laser light on it and create something unusual, so breaking the symmetry in light flow, and the symmetry breaking means you have a different stable state in asymmetric regime. So these state actually could be used as a carrier, like a soliton or optical bullet, or you can transfer information. You can make a sensor, you can make an imager, you can make computing, all these things, because there are a lot of interesting phenomena will happen in the light matter interaction within this cavity resonator. These interaction actually will give you the facility to create new thing, new physics. So it's the integrating challenge to study and understand of the light matter interaction at that length and time scale. So without further delay, I request you to Dr. Hills will explain the things over here. Thank you very much.
Okay, I hope everyone can hear me. Okay, first of all, I'd just like to start by thanking you all for the invitation here today and for that very nice introduction, certainly for the flowers. Actually, there's a common phrase that the first time a man receives flowers is at his funeral. So I hope this will be a more joyous occasion than my funeral. So yeah, many thanks again for the invitation. So yes, today I'm going to be talking about this topic, which forms the basis of my research for the past 7 years now. But as was introduced, this is of course quite a diverse audience. There are some people here from a technical background. But just so I know the audience, who here actually is coming from a technical background with nonlinear optics and who is a more lay person? If you could just put your hand up if you are from nonlinear optics. Okay, so about half the audience. Okay, that's perfect. Okay, so this talk, I'm going to start by actually catering to that side of the audience and introducing the actual fundamentals behind this research. Hopefully that way you'll all be with me throughout this presentation. I'm then going to go on to talk about this spontaneous symmetry breaking phenomena, first of all with something known as a ring resonator, and I'll talk about some of the very nice applications that we can find from this. First of all with counter-propagating fields, fields in opposite directions, and something to do with polarization. And then finally going on to combine all of this into a very nice single system. I'll then move on to talk about this phenomena in a different type of resonator, something known as a fabric pro resonator. Again, I'll introduce all of this throughout this talk, and especially focusing on something known as a temporal cavity soliton and the applications that that can have. Finally, to end this talk, which is approximately an hour long, I'm going to talk about how we can actually use this symmetry breaking to create something which only was recently discovered by ourselves of self-crystallizing solitons and some of the fantastic applications in industry that that can actually have. And then finally I'll summarize, and if there's any questions I'll also invite them. I think due to the nature of the audience, if there's any strong sort of technical questions, I will be here for the rest of the day and we can talk then. So perhaps we can keep the questions slightly more general just for the benefit of the audience. This is also work, like I say, from the past 7 years, so it's actually taken me around the world. I've worked at several very nice institutions. So my bachelor's background, my first degree in mathematics, the second in theoretical and computational physics, was at Cardiff University in Wales in the UK. Before then moving up to Scotland, to the University of Strathclyde in Glasgow, to complete my PhD in collaboration with the National Physical Laboratory, which is based down in Teddington in London. Over the years, I've had many fantastic opportunities through the use of scholarships, one of which took me to the University of Auckland in New Zealand, where I completed 6 months of research, which I'll summarize for you today. Of course, we've already mentioned the association with the Max Planck Society, but also this is work taking place in Dijon, in France, one of the CNRS labs, and most recently, only last month, I was a visiting scholar at the University of Concordia in Montreal, over in Quebec in Canada. I'd also like to point out right from the beginning that, of course, science is not a solo venture. Science is all about collaborations. You have to think about the people that came before you. So certainly my old professor of my PhD and still a continuing collaborator, Professor Jean-Luc Albo at the University of Strathclyde, my current group leader at Max Planck, Pascal Daré, but I'd also like to very much highlight the students that are helping me complete this work. So this is Graham Campbell, who will actually soon be defending his thesis. He's a PhD student still back at Strathclyde, but also most relevant to this work at Max Planck is the student Aleko Ghosh, which you can see here, and also Agadeep Powell, which is over here. So yeah, just bear in mind that a lot of the work I'll be talking about, I've been a contributor, sometimes a main contributor, but actually this is the work of many fantastic collaborators. Okay, so to start off, talking about the fundamentals behind this research. So first of all, asking the question, what actually is spontaneous symmetry breaking? And to describe this, I'm going to build up from a very basic definition, but also with an artistic diagram. So this is not scientific data, this is just an artistic way of displaying this symmetry breaking. So very basically, spontaneous symmetry breaking is when two or more properties of a system suddenly change from having some equality between them, they are symmetric, to having an inequality, i.e. they become asymmetric, following an infinitely small change to some system ground. So along this graph that I'm going to build up for us, Along the y-axis we have some system properties, P1 and P2, and along the x-axis we have some system parameters. So this is you in the lab changing something in the experiment, and we will scan across this x-axis. So to start with, perhaps we have these two properties which are evolving no matter what we change this parameter. They are always equal to each other. So you can see from the definition we're in that symmetry regime. However, if we continue to change that parameter, you see that we have this bifurcation event, where one of the properties or the other takes this dominant path and proceeds up here, while the second becomes submissive and becomes lower in terms of whatever that property value is. This is when we have moved into the region of asymmetry, and very obviously you can see that bifurcation point where an infinitely small change to that system parameter will move back and forth between the symmetric and the asymmetric region. That, quite simply, is the spontaneous symmetry breaking bifurcation point. Now, in many systems, not all systems, but actually if you continue to scan that system parameter, you may actually go back to a situation where you've returned to the relationship where P1 is again equal to P2, we have returned to symmetry, and in this case we have an additional bifurcation point which we call spontaneous symmetry restoration, for very obvious reasons. Of course, if we were scanning the system parameter in the other direction, this would become the breaking point and this would become the restoration point. But either way, there is symmetry breaking or restoration bifurcation points. An important thing that I'll quickly explain to you all as well is that quite often there still exists a solution where those two properties maintain their symmetry. So they are still symmetric to one another, but this is what quite often is known as dynamically unstable. And I'll go on to talk about that right now. So the easiest way to introduce as technical people in the room the difference between stable and unstable solutions is actually by considering something very basic, which is a pendulum. So everyone knows what a pendulum is. You see it in the old clocks. But just in general, I'll describe the pendulum as, in this case, a solid, for example, a string with a mass on the end. And the important thing is that in this case, this pendulum is rigid. So, if we take that pendulum and we just have it in this nice stable situation, just because of gravity, the pendulum finds its place, and we introduce a perturbation. So a perturbation is simply I give the pendulum a quick push. Everyone knows, okay, you have disturbed the pendulum from that center position. What's going to happen? The pendulum will then begin to swing back and forth, and it will evolve over time until eventually it will settle back to that state where the pendulum is in the exact same state after its evolution as it was in the beginning. Because that initial condition was perturbed and then returned to its final state the same as the beginning, we say that this is a stable state. No matter what is done to this system, it returns following its evolution. However, there is actually a second stationary state to the pendulum, and that is when the pendulum is actually directly with the orientation pointing upwards. This system is now the opposite to a stable state. If we were in a very well-controlled lab, where there is absolutely no noise, there is no wind, no air resistance, nothing interacting with this system, then the pendulum would stay in that perfectly vertical position for all of time. However, as soon as there was any noise in that lab, which of course there is always noise in reality, then that pendulum, which will then become perturbed, will immediately swing back down, and it will then begin to oscillate just like before, so that the final state of that pendulum is actually different to that initial condition. So this is what I mean by an unstable state. An unstable state in a dynamical system is if it experiences any perturbation, any noise, any, in this case, wind, anything, even the slightest amount, it will then move away from that unstable state. So in relation to this figure, effectively in any system, which is always reality, you will have noise in your system. So although this symmetric solution exists, if we were magically able to sit here and then introduce noise into the system, the symmetry would immediately break and it would evolve so that one of the properties moves up and one of the properties moves down. Okay, so that's artistically what I mean by spontaneous symmetry breaking. I'm now going to go on to talk about the two main experimental systems where we can actually use this symmetry breaking for some quite nice effects. First of all, I'm going to introduce the ring resonator, and secondly, what's known as a fabric resonator. So to start with, the ring resonator, it is named as such for various obvious reasons. It contains something which is this circular or repeating path. And this system, theoretically, is actually very easy to explain. You can see that it involves some laser input. This is of course a light source which sends light along this path, and then you then have some two-way exchange. A two-way exchange can be achieved by a couple of ways. This is slightly technical, but in fibers you can achieve a two-way exchange with just a fiber coupler, or with micro ring resonators. I'll talk about in a second. You can achieve this with evanescence. But for the less technical people in the audience, all it means is that light which is propagating along this path has the option to jump onto this second path. And equally, light which is propagating along this path, it has the option to jump back on towards the path, which then leads to some either use or measurement. The important thing about these resonators is the material which makes up this ring part is what's known as a Kerr material, something which exhibits a chi-3 nonlinearity. Again, this is something I will very basically introduce in just a second. But for the lay people in the audience, effectively, this is a special type of material, or at least a material in a special parameter space. Now, the Fabry-Perot resonator, on the other hand, is actually a very similar system, but with one main difference. As opposed to having that ring, which allows light to propagate in this circular direction, now a Fabry-Perot resonator is made up with two mirrors, such that the light which enters the resonator will bounce back and forth in a linear fashion, so along the same line, before eventually leading on towards our output. So fundamentally, these two resonators are very similar, but actually they have these different optical paths which introduce some complexities which we need to later model. So some assumptions that we have about these systems. First of all, we assume that we are dealing with high Q resonators. So what is a high Q resonator? It means that there are not many losses in this system. They are very high quality factor. Second of all, we assume that those transmissions, so either this mirror, the light that enters, or the light that exits, and again with this two-way coupler, there is a very low transmission. So what is a low transmission? It means that if you were riding on this, the wave of the light, there is a low probability that you will cross this transition. So the majority of light will just pass through, never interacting with the resonator, but there is a very low probability that light will enter. But these probabilities of moving back and forth, they are two ways. So that means even though it is highly unlikely that you will enter the resonator, it also means that once you are inside, there is a very low probability of exiting. So the combination of these two assumptions, high Q resonators and these low transmissions, means that we have a very high number of round trips. So light that enters will proceed to propagate for millions of round trips before eventually leaving. The reason these resonators are so useful, especially in industry, is because actually this means that the build-up of the nonlinear interaction, so when light is interacting with the material, you can effectively create very large amounts of that nonlinear build-up over a very short space of time. Effectively, by having this circular path, you are recycling the same material, so you can achieve very high nonlinear effects with very small amounts of physical space. Okay, so those are some theoretical diagrams for you, but here I actually have some real-world realizations of these ring resonators. So first of all, we have what's known as a microtoroid resonator. So here we can see the resonator is at the top here, and it sits almost like a mushroom on some base. Here we have a silicon nitride resonator, which you can see both of these resonators are extremely small on the micro level. Here, instead, we have a larger type of resonator, which is actually made from a rod of glass. So this particular example is about 3 millimeters in diameter, and you can see we've actually highlighted that input-output waveguide with just a red light in a minute. And you can see that even though light, let's say, is coming in from over here, you can see how it's bouncing around the edges of this circular ring resonator. At the bottom here, I actually give an example of using a fiber to create these resonators. So this is actually a fiber ring cavity, and you can see here that now actually you have 85 meters worth of fiber wound up to create this ring resonator. So here you can see the two big differences in size, one of which is taking place on the micro scale, another of which is using close to 100 meters worth of fiber. Some examples of the fabric Pramod on the other hand. Here again we have that input-output waveguide, and then in the middle we have, with that theoretical picture, the fabric Pramod. So these dotted parts, this is actually a way of creating the mirrors, with a close-up of those mirrors here. But fundamentally, for those in the audience, you can think of these bits at the edge as just mirrors, and light is bouncing back and forth along this path between those two mirrors, and then eventually exiting and entering by this waveguide. The example on the right, however, is actually creating this fabric Pro using an optical fiber. So here we actually have the rag mirrors installed and actually coated onto the front of the fiber, so that again light can enter by one side, bounce back and forth along these two pieces of fiber, again for an extremely high number of round trips, recycling that material, and then eventually leaving on towards the output, either for use or for measurement. Okay, so I said that this is something which is taking place in this special material, these Kerr materials, but what actually is a Kerr material? Well, this is slightly technical, but I think this is the easiest way to explain it. So the easiest way to understand the difference between a Kerr material and what's quite normal as a linear material is actually looking at how the atoms in the material actually have displacement and polarization following an electric field. So these are two blocks of material that I've put on the screen for you. They're dielectric material, and these nice little purple guys within this material, they are the non-polarized atomic elements, so the atoms that make up the material. The block on the left we're going to leave alone, we're not going to do anything to it, but the block on the right, we're just going to have some electrical field, which is across this material. And the effect of that electrical field on those atoms which exist within the material is actually then the atoms become polarized. And the amount those atoms are polarized depends on the type of material. So in this case, looking at linear materials, there is a linear relationship between the electric field and the amount of polarization which is taking place. With nonlinear materials, which is the type that are a focus in this presentation, instead of having that linear response, we actually have a nonlinear response. So a nonlinear response simply means, and sorry for the mathematics, but a nonlinear response simply means that the amount of polarization you're experiencing, rather than just being the same order with the field, actually there are higher orders, so square terms and cubic terms, many other terms. Specifically with our Kerr materials, we only are considering the cubic nonlinearity. So we have the linear response, but also this cubic response. Like I say, this is a slightly technical scale. The reason this isn't ordinarily seen without laser light is that typically these higher order effects are actually very weak. So almost always we see this linear response in the atomic polarization to that electric field. But you can see here that actually a cubic term, because of its nature of being cubic, as the electric field increases to high intensity, i.e. with lasers, actually the Kerr effect can take over. So even though it starts off extremely weak in comparison to the linear line, you can see that we can actually reach a point where not only does it become comparable in strength, but actually it can exceed quite greatly that linear. So this presentation, yes, is on these Kerr materials. But for those of you who perhaps are lost with this slide, Kerr materials are special types of materials. Okay, so with that, I think now we can understand all of the things that are taking place in these two diagrams. So the couple of things to remember, we have this special material, this Kerr material, we have these assumptions which experimentally we fabricate these and these assumptions hold up. And there are differences between the ring resonator, where light is proceeding in this circular way, and the fabric Kerr resonator, where light is bouncing back and forth along the same material. Okay, so how do we actually model these two systems? One of the most celebrated models for its speed, but also actually its accuracy, is the so-called Lujato-Lefevre equation. And before going into the mathematics of this equation, I'm actually going to stick just to the physical phenomena for now. So you can see that this equation is fundamentally made up of 5 components, and these are 5 different physical effects. So the equation itself is modeling how does the field which is circulating within the resonator, how does the field evolve over time? And I've called it slow time here, I'll come back to what I mean by slow time, but the field which has entered the resonator, how does this actually evolve with all of these physics that is taking place? Well, the physics that's taking place are these remaining 4 boxes to the equation. So the first thing, of course, that we need to consider is how much light is actually entering into our resonator. So we need to take into account in some way the laser input. We also need to take into account how much energy is leaving the system. So this is energy that's leaving via that output, but it might also be, even with these very high Q factors, there might be some losses which are escaping via the resonator. We then need to take into account something known as dispersion. So this is something in physics that if you have some shape within your system, it will disperse the shape. And then finally, we need to take into account the nonlinear effects. So when the light, which is circulating, interacts with the material, how is that changing the properties of light? So this is the nonlinear effects. So this is what the equation actually looks like. And this might scare a few people, but actually this is not too difficult. This is quite a simple equation. We just have quite a few variables in there, which are just algebraic terms. So E is just the electric field, the field, circulating field, which is actually going around the resonator. Here we go, E. We have this time variable, slow time to start with, that input pump. A is the focusing type, so these things are a bit technical, but the type of focusing that the material is actually giving to the light. We then have this cavity tuning variable, so this is actually quite simple. The cavity tuning is just the difference between the frequency of the laser that's going into our system and the closest cavity resonant frequency, so how many full wavelengths will actually enter into our resonator, and what's the difference between them. That's the tuning. Finally, we have the type of dispersion, either normal or anonymous, and then we have a second time scale. So now just to break down these 2 different types of time scales, this might be a bit confusing. How can you have 2 time variables? Well, the fast time scale, as the name suggests, is actually taking into account how does the field change on a single round trip of the resonator. So for example, you might have some structure in the light, which is only there as it's propagating around the resonator. But the slow time scale is actually how does the entire field profile evolve over many round trips. So as I was saying, the light can stay in the cavity for a very long time. So that actually means that the profile of the field around the resonator can actually experience many dynamics once it's been in there for quite a while. This model actually was first derived back in, it was adapted in 1992 for these ring resonators. So this is actually a very well-established model which is held up rigorously to experimental verifications. The Fabry-Perot resonators that I've just drawn on the screen for you here, fundamentally very similar system, but actually it has some complexities in it, which meant that the model to describe the Fabry-Perot in the same way as Fujata-Perfet, it took nearly 30 years to update the model. So this is actually quite surprising when you see that fundamentally these 2 equations are the same.
Slow time means that acceleration of the individual what?
Slow time means that the entire field profile which you have within your resonator, as it is completing multiple round trips, it can actually evolve. So that
evolve in terms of what? Phase, intensity?
Phase, intensity, all of these different properties of the system, it can actually evolve through these different physical effects. So if you can imagine you have a certain intensity of light in your system, but then more light is being added to it, then it's going to get stronger, or if more light is leaving, then it's going to get weaker. So that's something that will build up over time. Okay, so the Fabry-Perot resonator fundamentally exactly the same type of equation. So you can see that actually the physics is relatively unchanged. We still have these 5 boxes, the evolution over time, the inputs, the losses, dispersion, and the nonlinearity. But you'll note that this box is bigger than this box, so that it probably implies there's a bit more complexity going on. The reason for that complexity is that when light is circulating in the ring, if we imagine this is the forward part of the field, as it's making its return journey, it's actually in a different part of the system. So the light that's propagating on this side, it doesn't see or interact with the light that's going in this direction. However, in the Fabry-Perot, because the light is bouncing back and forth along a straight line, the light which is propagating forwards will start to interact with the light that's propagating backwards. So there's actually a complexity which leads to very interesting phenomena later on. This is actually very simple in the end to model. It just took 30 years to realize how simple it was. All you need to do is take into effect the average of the propagating field. So as the field is propagating forwards, it will interact actually with its entire tail. So this actually, it looks difficult, but this is actually just an integral of the field profile over an entire boundary. So you take into account the average of the reflected field. And I'll come back to why some of the unique properties of the Fabric Pro are precisely down to that reflected field later. Okay, so I think that mostly covers the fundamentals that are needed for this presentation. And I've introduced artistically what I mean by the symmetry breaking. I've introduced the systems, and now I'm actually going to show how we can get this spontaneous symmetry breaking in these resonators, and also why this is so useful for various applications. So first of all, I'm going to focus purely on the ring resonator. So we'll talk about the Fabric Pro resonator for now. So the ring resonator, again, I'll put on the screen for us, but you'll notice something different about this picture. In this picture, rather than just having one input and one output, now there are two. And one sends light into a counterclockwise direction, and the other one is sending light in the opposite direction, going in the clockwise. So now within our resonator, we have got two fields which are circulating, field E1 and E2, just to give it some mathematical variables. So some more assumptions that we have about these systems, and these are experimentally valid assumptions, or at least you can create these to be valid. So we assume that we have balanced inputs. And what I mean by balanced inputs is that those two laser sources, input 1 and input 2, they have the same intensity, or the same strength. We also assume that they have the same frequency, so effectively the same color, and this means that the tuning between the two and the cavity is going to be the same. And something come along later, we assume they have the same polarization as well. We're also going to assume, to start with in this talk, that we have purely homogeneous fields. And what I mean by homogeneous fields is that effectively light which enters the resonator at that coupling point, so the point 0, and light which has completed an entire round trip, let's go back to this variable 100, it is very boring, it is just a flat profile. This is just what we're going to assume just at the start of this presentation. Very nice thing about when we have these homogeneous field intensities is actually we don't need to care about dispersion. So we can immediately just eliminate one of the terms from our equation. So those equations that I presented earlier, those 5 boxes, they're actually going to become common across this presentation. Again, we just have those, in this case, because we killed the dispersion, we still just have 4 boxes describing the physics of the system. However, you'll now note that rather than just having one equation, we actually have 2 equations. This shouldn't be surprising, we've got 2 fields, so we want one field to describe field E1, and the other equation to describe field E2. But the important thing to note about these 2 equations is that indeed they are coupled equations. All that means is that in the equation for field E1, there is some variable to the field E2, so the effects of the second field, and similarly in the other equation, there is also the effect of the other field as well. All this means in terms of the physics that's happening here is that the 2 fields, as they are coexisting in the system, they are just interacting with each other. This is just a mathematical way of showing that. So field E1, as it's propagating, it's going to be talking to its friend, field E2, and they're just going to be communicating as they are traveling around our resonator. So what do the solutions to this system actually look like? So if we find the stationary state, now we will start to see the symmetry breaking. So here, just like in that artistic picture, we have those 2 system properties, which in this case are the powers, or the strengths, of those 2 circulating fields. And along the x-axis, what we're changing in the lab. On this figure on the left is the input intensity, so that's you in the lab turning up the strength of the laser. And on the right, we are varying the cavity tuning, so that's you maintaining a constant strength of laser, but changing the frequency of the laser. You'll note that these solution sets are colored, some of them in blue, some of them in red, and this is just to differentiate the symmetric solutions and the asymmetric ones. So you'll note that to begin with, for low input intensities, and also for the low cavity tunings, we just have the blue solutions. So this means that for the majority of this figure, the two fields are propagating with the exact same strength. This is of course very intuitive because you have the same inputs. If the two inputs are sending light in opposite direction with the same strength, you expect the two fields to then circulate with the same strength. And that's exactly what happens when we're in this region below the symmetry breaking threshold. But once we reach a certain threshold, and this is parameter dependent, you see that now one of the fields actually intensities becomes very strong, and it starts to steal energy from the other, and the other field becomes submissive and becomes very weak, so that now we have broken the symmetry, and let's say in one case, the clockwise field suddenly becomes incredibly strong compared to the other, which becomes weak. We actually see this exact same effect when we're varying the frequency as well. So again, we are on this nice symmetric solution, the two fields are equal, and then one of them takes this dominant path, and the other one takes the submissive path. Okay, so this slide very much is only for the technical people in the audience, and it's just a very brief introduction as to where this actually, what causes this phenomenon. So quite often, exceptional points and symmetry breaking are ubiquitously found. So this means, like I say, this is just for the technical guys in the audience. This effectively means if you look at the eigenvalues of the dynamics of this system, the place ordinarily where you see that spontaneous symmetry breaking, where the two properties, one becomes dominant, one becomes submissive, coexists in the same parameter space as where an exceptional point, where two of the eigenvalues suddenly become equal or unequal to each other. What we actually find in our system, however, we're currently writing a paper on this, is that we have a dislocation between these two phenomena. So the exceptional point, which is occurring in the eigenspace, is actually dislocated in terms of the parameter space to the spontaneous symmetry breaking. And you can actually see that here. This is the real part of the eigenvalues, and you can see this is where we have an exceptional point. One of the eigenvalues moves up, one moves down. You can see that the point where we get the symmetry breaking is actually dislocated in parameter space. So after this talk, probably don't ask me any questions on this in front of everyone, but we can talk, if you're interested about this, just one-on-one, because this is quite a technical part of this research. Okay, so now that we've had the technical part of the research, I'll go back to actually some of the interesting parts, which is of course the applications. Where is this symmetry breaking actually useful, both for science but also for industry? This is just a sample of the applications that we have found for this. So actually, because we have this difference which occurs between the different directions, actually it's extremely useful in things like optical gyroscopes. So for example, if you're trying to stabilize a drone or something like this, actually you can enhance the so-called Sagnac effect, which is used for measuring rotation using this spontaneous symmetry breaking. The spontaneous symmetry breaking can also be used in things like all optical computing, photonic integrated circuits, creating logic gates and also memories in multiple ways. Because you imagine you have these two states in the system where one of the properties is dominant, one is submissive, but equally the other one could be dominant, the other one could be submissive. This then can become a 1 and a 0, so you can encode data in this way, or you can create logic gates where when you're in state 1, which is the clockwise field being dominant, and you program a certain thing, when the other one is dominant, the other happens. But actually something that I'll go on to talk about again later is in this very nice application of actually with frequency cone generation. Frequency cones I will actually introduce later, but they won the Nobel Prize, I think, back in 2005. And frequency cones can effectively be thought of as rulers, but rather than measuring distance, they are used to measure frequencies of light. But I'll come back to this. So as you can see, this isn't a phenomenon, this symmetry breaking phenomenon. This isn't just something which is theoretically interesting. This is something with real-world application, and not just one or two applications, but a diverse range of useful applications for this research. Okay, so moving on from counter-propagating light, I'm going to be talking about symmetry breaking with orthogonally polarized light. Polarization is a slightly difficult thing to explain to a lay audience, but effectively, to the technical audience, it means that, okay, the polarization is going in this circular fashion, one component is going in the left direction, one going in the right direction. For the lay audience, all you need to understand is that there are two components of light propagating in our resonator, but rather than propagating in opposite directions, they're now going in the same direction. So you've just got two light fields coming from a single source going in the same direction, and they still interact. Okay, so in this case, we're going to relax some of the earlier assumptions, and we're just going to say that, okay, this light source for the technical audience is linearly polarized. That allows us to create these two circularly polarized components within the resonator. Again, for the lay audience, all you need to think about is that there are two components co-propagating the resonator. So the same boxes appear once again, even though we're dealing with a different system. Now we have co-propagating light, this polarization effect, but it's still the same boxes. In this case, we actually still have the coupled equations, so the two components in the system, they're always talking to each other. We have the effect of the second field appearing in the equation for the primary field, all of this. But now, we still contain the exact same type of results, where we obtain these very nice symmetry breaking results. So this just means that those two components which are co-propagating, one of them becomes dominant, one becomes submissive. For the technical audience, means that, for example, the right polarized light can suddenly take almost all of the energy from the left polarized light, or the other way around. So this allows you to break the symmetry of the polarization components within your circulating fields. The nice thing is that because they are co-propagating, they are going in the same direction, actually now we can relax that condition of homogeneous fields. So now, rather than having that flat profile that never changes throughout a resonator, which is very boring, still useful, but boring, we can actually allow for the field to change as it propagates. So this then, this technical word for this is an inhomogeneous profile. So rather than being flat, homogeneous, it has, for example, spikes or a pattern, some variation in the field across the resonator. So I'm going to talk a bit about these inhomogeneous field profiles. And I'm going to focus on temporal cavity solitons, mostly because they're fantastic application in frequency noise. Temporal cavity solitons are actually a very nice thing for me to talk about, completing my PhD in Scotland, because actually temporal cavity solitons are a Scottish invention, discovery I should say. And actually they were very first observed by a Scottish engineer back in the 1800s, actually looking not at optics or nonlinear optics, but actually at fluid dynamics. And this is the best way to introduce a soliton. You've perhaps all encountered solitons. If you've ever taken a bath, you get in the bath, you see the water suddenly move in one direction. And that's exactly what John Scott Russell observed actually riding along the canal in Edinburgh. And he saw that as a boat, or any mass, is entering into the water, it will create this solitary wavefront. So not a sine wave which goes up and then down again, but a soliton is something which is only going up. And this then pushes the water along that canal. And what, as the story goes, John Scott Russell did is he actually rode by horseback and he followed this soliton along the canal. And he observed that this soliton maintained both its velocity, so its speed of propagating along the canal, and also its shape. And this effectively became the definition of the soliton. So a self-reinforcing wave packet that maintains its shape while it propagates at a constant velocity. So that was in fluid dynamics, but actually much later, these temporal cavity solitons were observed in optics. And here I show the nice ring resonator, which you will see many times in blue. And this red along the top is just a representation of the intensity of the field profile around that resonator. So if we were dealing with homogeneous fields, it would just mean, okay, we are flat along the whole thing. But here you can see we are inhomogeneous, because even though for the majority of the resonator, the field intensity is constant, we see this big spike in the field intensity at a specific point. This is exactly what's known as a temporal cavity soliton. Temporal cavity soliton existing in the time domain, that simply means that as the field profile is rotating around the resonator, you would see this spike come out if you were looking at it in the time domain. But of course, we can take anything in the time domain through a Fourier transform and look at it in the frequency domain. And now you see, for the first time in this presentation, the optical frequency cone. You also see why an optical frequency cone is commonly referred to as a ruler for light, because you see that the frequency cone is made up of these many equidistantly spaced peaks. And this is exactly like if you looked at a ruler, centimeters, millimeters, you see these markings on the ruler which are equidistantly spaced. So actually you can use the frequency cone to measure the relative frequencies of different properties of light. So like I say, this was just as transformative in metrology of frequency as the ruler was for measuring distances, and won the Nobel Prize in part in 2005. Now there was some controversy around whether or not these temporal cavity solitons actually existed in the first place, because these temporal cavity solitons usually exist in conservative systems. This means that all of the energy that's in the system is maintained. It cannot leave, it cannot exit. But we know that that's not the case for these systems. We have an input pump and we also have losses. So at the beginning there was some debate as to whether solitons could actually exist. But the reason why they certainly can exist within our system is because of multiple balances taking place. So actually all of the energy that is lost from the system can be balanced by the energy that's going into the system. And that way it maintains some of these conservative properties. And equally, even though we know we have dispersion within the system, the dispersion itself can be offset by the effects of the nonlinearity. So we can create this stable structure which will propagate around our resonator by having these multiple balances all playing off each other. Okay, so let's have a look at these temporal cavity solitons. So this was work that was completed while I was at the University of Auckland in New Zealand. And we were looking at, okay, these soliton profiles, can they experience spontaneous symmetry breaking? So symmetric temporal cavity solitons here, even though we've got these two field components, you only see one line. And that's because the field profiles, where the spikes and the intensity of the fields is occurring, they're actually occurring in the exact same places. So both profiles are solitons in the exact same place, and not only in the exact same place, but at the exact same strength, so the exact same intensities. However, what we found is that actually we can observe asymmetric temporal cavity solitons which have undergone this spontaneous symmetry break. Something which is very important to note for later on is that in this particular case, we have this pair of solitons where the orange field, whatever that is, clockwise propagating, or right circling clockwise light, is dominant in the first case, and the blue field is submissive, but in the next pair, and also the next pair, actually it's the blue field which is dominant, while the second field is submissive. So actually there's no conditions in this particular system as to which of the fields is dominant in our soliton profiles. Either one can be dominant, either can be submissive. These things actually you can model very easily. Just solving those equations. For the technical people in the audience, we can use the split-step Fourier method to integrate these types of equations. And you can see that even though we started off with a symmetric soliton, because the symmetry breaking case, these are unstable, you can see that the system is currently evolving, and eventually it will stabilize, but it will stabilize rather than having symmetric solitons. It might be a bit small on the screen. You can see that now one of the solitons is much more submissive, and the other field is much more dominant. So actually one of the proposed applications of this research was that you can imagine you can have many of these solitons existing along your ring, and when the blue field is dominant, this can be a situation of 1, and when the other field is dominant, that's a situation of 0. And because these solitons, as I showed on the other slide, there's no strong interaction between them. This means that actually you can encode, theoretically, bits of data along your ring resonator. So actually you can store data within these resonators with a very high rate of both accessibility, but also of writing of the data. Okay, so here is actually just a bifurcation diagram where, in this case, it's just showing the symmetry breaking of the soliton itself. So rather than the flat profile here, we just have peak of the soliton. You can see we have a region of symmetry solitons where they are just overlaid on top of each other, and then we get this nice bifurcation where the solitons enter into that asymmetric state just by changing the frequency of the laser. Okay, so I mentioned that these solitons, they can oscillate in our systems and eventually they can stabilize, but actually there's something to be slightly wary of, or perhaps useful for other ways, which is that of a breathing soliton. So breathing solitons are actually solitons where the peaks of the solitons, they don't stabilize. They actually keep oscillating indefinitely if you carry on your system. So you can see here, we're just tracking the peak of that soliton, both the dominant and the submissive, and you can see that we actually get this very nice, regular breathing of the soliton. The peaks are going up and relaxing, But actually something which is very useful for anyone who is interested in chaos and the applications of chaos, actually we can also have much more irregular breathing. So here the solitons are actually oscillating in a very interesting way, where they're actually periodically interchanging their dominance. So to start with, the blue was dominant, now it is red, and now we've just observed a second switching event where the blue has become dominant again. The reason this is quite an interesting set of dynamics is that you're in a forward direction, and then when they're reflected, you also have two fields going in the backward direction. And again, they're differently interacting with each other. But they're explained by the exact same types of equations. We've still got just those 5 main components. The only difference is now with nonlinear effects again are complicated. So we have the couple equations, which are the two polarization components in the fields. However, we have to take into account not only the interactions between the co-propagating components, but as I explained at the beginning, we also need to take into account the averages of the fields. So this field, as it's propagating forward, it interacts with the average of the backwards and forward propagating fields. And we have that energy exchange as well. However, if we first consider homogeneous fields, the average of anything which is consistent is just going to be the value at any one point. So in terms of homogeneous fields, all of these equations revert exactly back to the ones that I've already described. And so even if the system is complicated as this, you can still observe the fundamental spontaneous integrating results taking place. So that's fantastic, but the true intricacies of these systems come when you think about telepathic solitons and the inhomogeneous profiles. So as I mentioned earlier, this was an important thing to remember. In this ring resonator case, all of the soliton pairs, they didn't really care about each other. In this soliton pair, the orange field is dominant, the next one is blue, it's entirely independent of one another. When we ran similar simulations with the Kerr Resonators, the first time we ran it, we were like, oh, we're incredibly lucky here, because all of the soliton pairs have the exact same dominant component. But every time we ran the simulation, this kept happening. So even though in the ring, the solitons, they had no way of interacting with each other, so they were completely random in polarization. Here, it was implying that somehow the solitons in the system, they are looking around at their friends, and collectively they are agreeing what polarization they're going to have. So it implies that there is a way that the solitons are actually interacting with each other. We really wanted to investigate, okay, how robust is this effect? Is the system actually always doing this to be deliberately perturbed? Are we going to be able to cause that non-conformity? So we took the system, in this case, 4 solitons, and we were just tracking one of the soliton profiles. So you can see that to start with, this is just time along the x-axis. These are stable solutions. They are not changing. However, at a particular point in time, we decided, okay, we're actually just going to go into the data and we're going to deliberately swap the profiles. In the ring, that's no problem. That is a stable solution. When we did it with the fragment Kerr Resonators, so we changed the first one and also the third one, you can see that we did this at point 25, and immediately you can tell the system is not happy. And immediately the system rejects this non-conformity. And then immediately the spikes of that soliton will begin to oscillate, and eventually the stable state, when we do find a stable state, is actually something different. And if we look at that, it's actually returned back to the conformity state. So this shows that actually the solitons in these fragment Kerr systems actually have this polarization of conformity that doesn't exist in the ring. Again, you can think of many useful applications of this, such as encoding data if you want to be resistant to noise. So if you had a chain that say 3 solitons which had that binary 1, 0, all of those solitons should be exactly the same as each other. They should have the exact same polarization. But you created them in a system which guarantees this polarization conformity. But then when they're sent along the rest of the system, if suddenly one of these is swapped and it becomes 0 and 1 rather than 1 and 0, you can look at the neighbors, and if they are not consistent, you know your data is correct. The reason that these solitons have this strange ability to talk within the system is actually exactly due to those averages of the fields. Because effectively, by allowing the soliton or the system to observe its average, this effectively means that as the soliton, let's say, is passing along our resonator, it has the ability to see or feel the effect. each other and they can build out that conformity within the primary probe. The reason this doesn't take place in the ring is because, I don't have a picture of the real screen at the minute, but to imagine the field which is entering the resonator, it propagates upwards on the right. As it's propagating back down, it's taking place on the left. So the two fields never have a chance to see what's happening in their profiles. But in this case, the fields will see their own profile via their tail in that reflection. Okay, so what do we talk about? And okay, so that brings me to the last part of this talk, which is one of our most recent discoveries, which is this topic of self-crystallizing solitons and why these are so useful for things like frequency generation. So to do this, I'm just going to very quickly introduce what I mean by a soliton crystal. So in the pictures I showed earlier, we have a nice ring resonator field profile on top, and we only have a single soliton in the system. But what I mean by a soliton crystal is when, okay, we have multiple solitons within our system, and we want to define some kind of unit cell that we can then say, okay, this is the crystal that we're using. In the most basic case, actually you can define a unit cell as just the entire cavity, because actually the cavity is just a so from the start to the end, even though these solitons are very irregularly placed, it's still a crystal because actually you can define a unit cell, which is just the entire profile of the cavity. However, this is not so useful. So we call this an irregular soliton crystal. The distances between the solitons is quite arbitrary. Another thing I'm going to talk about here is that as much as we have those solitons where they sat on a very low intensity background, and we have that very high intensity peak, we can actually have the opposite, which is a soliton which has a very high intensity background, and the soliton itself is this very sharp drop. So we differentiate between the two by calling these dark solitons. And so again, we can have these dark soliton crystals where the unit cell is the entire cavity, and again, this is an irregular dark soliton crystal. But the big question we really want to make use of these soliton crystals is can we create regular soliton crystals where every single one of those solitons is equidistantly spaced along our cavity? And if the answer is yes, can we actually go between the two? So can we move from this irregular soliton crystal to this regular soliton crystal? And here you can see that now we can actually define a unit cell which is much smaller than the cavity. If you think about the industrial applications of this, the reason this is so useful is because actually there is going to be a limit of how small you can create your cavity. So whatever that number is, we call it 10. So let's say the length of the smallest cavity is 10, and so the repetition of that unit cell will occur every 10 lengths. But if we can actually create a unit cell which is much smaller than that, and this itself is repeating, this is effectively reducing cavity length. So we can go from something which is at the limit of what you can reduce, but the repetition rate can actually be reduced even further by achieving the soliton crystal. But can we do it? And the actual answer is yes, if we use the spontaneous symmetry rate effect that I'm talking about. And this was a very surprising result for us. So the reason we can do this is because, again, we can get the symmetry gradient of a pattern state. So you can obtain what's known as a Turing pattern across the resonator. And if these were symmetric patterns, that would mean that the two field profiles, the patterns are just completely overlaid on top of each other. But here, you can see that these are symmetry broken. One of the fields is completely out of phase in terms of the Turing pattern to the other. So this was nice, symmetry broken Turing pattern. However, with this dark solitons we talk about, we also know that these can exist in the system. So the question that we were thinking about is, can they coexist? Can we have a combined solution of a dark soliton and the symmetry regulatory pattern? And what we find is that actually in some systems, this is perfectly valid. And the reason this was such a nice discovery for us is because these Turing patterns, they act a bit like springs. And so here, we have a system where we've just got irregularly spaced solitons. And the frequency code, the technical frequency, you can see that this is very spiky. This is not a very clean code. But if we move into a parameter space where we can induce Turing patterns, so here we are evolving in time along this x-axis downwards, you can see that immediately the troughs of the solitons, which are dark blue, they immediately begin to move. And Turing patterns are evolving so that they are actually pushing the solitons throughout the system. And this means that actually what ends up happening is that all of the solitons in the system end up being equidistantly spaced along the rest. We have self-created a soliton crystal. And you see the beautiful frequency band that you get out of this. Not only are these very smooth, and by the way, you can actually even eliminate this extra peaks just by killing the pattern going down. So not only is it very smooth, but actually if you look at the numbers, the peaks of the code are actually much stronger. So you've actually not only cleaned up your code, but you've also enhanced the strength of the code itself. There is a limit to this partial crystallization, where effectively if the solitons are too far apart, then just like a spring, if you pull a spring too much, you will then just bend the metal and no longer is a spring anymore. That same effect can happen. But in that case, you just introduce more solitons into the system, and you will still obtain that soliton crystal. I won't go into the maths of that yet. We prove effectively what the maximum spacing can be, and how we can introduce more to create that crystal. Okay, so with that, I'd just like to summarize this talk. I'd like to thank all of you for taking the time to listen to it. So we've covered quite a lot. We've covered the fundamentals and the sort of artistic picture of the symmetry breaking, and Kerr Resonators, how we actually model these using the LLE, which are the variation. We've spoken about spontaneous symmetry breaking in a couple of different systems, so in the ring systems, also in the Pro systems, and what happens when you have counter-propagating fields, orthogonal fields, this separation from exceptional points. I've discussed briefly some different applications of this work, but as I say, it's just a selection of applications. And then finally, we've talked about these temporal capture solitons, both in the ring, Fabric Pro, how we can actually obtain these self-crystallizing solitons. One thing that I'll very quickly end with is that as long as perhaps as boring as this lecture was, actually that was just a selection of the results that we've done. In recent months, actually, we've created new logic gates for integrated circuits. We have shown what happens when we actually couple multiple of these resonators together, so in this case with some nice glass rods. And we've also studied something known as CRO, which is a couple resonator optical waveguide, which is expanding on separating having multiple resonators, actually into chains of resonators, and we've shown how actually then we can have this very strong control of the distribution of light across the entire chain of resonators. And finally, the guys Jean in France, we've also shown something we believe to be a brand new type of localized temperature structure, which has been called the photonics. Which is where instead of having a soliton which is occurring always at the same place, you can actually have this splitting of profiles so that they are still locked to each other. One cannot exist without the other. But this is a brand new localized structure in our systems. So with that, I'd just like to again thank all of you for taking the time to listen. One of the papers that I've spoken about and a few others are available on Google Scholar. And with that, I'd just like to invite any questions that you may have.
Is it possible that this effect happens in case of negative sign of the nonlinearity?
Theoretically, very easily. Just put a minus on that. Physically, to have a negative nonlinearity, I'm not so sure. But in terms of pure theory, pure mathematics, you could do this, and then actually you see these types of symmetry breaking bubbles effectively occurring in opposite parameter spaces. So it becomes very invisible because, for example, you will start to see the symmetry breaking at negative intensities, which is of course not possible. But yeah, so effectively all of these phenomena, theoretically, they can occur at those values. So if there is ever some breakthrough where you have this negative nonlinearity, the intensity symmetry breaking would not work because there is no such thing as negative intensity, but negative cavity tuning certainly still exist. Yeah.
Because negative nonlinear, defocusing, with intensity the refractive index decreases, yes, like some liquid crystals. And also the second question, is there any limitation for the how fast must be the nonlinearity? Because you assume that it's electronic nonlinearity, yes, but could be made in liquid crystal medium with reorientation nonlinearities.
I think it depends if you are looking at the fast time effects or slow time effects. So the solitons and things like this, they are taking place within a single round trip, so then it might encounter some problems. But when it is just the homogeneous, which is all you need for the symmetry breaking, then these things can be much slower, because actually these building up over many, many round trips anyway. So yeah, I think in that case it should be still fine.
Okay, thank you.
Okay.
I was thinking from a perspective of the product, you mentioned that it can be used as a switch between the symmetric state and the asymmetric state. Right? So at that state, what frequency or what speed are we talking about for switching?
The speeds are entirely dependent on the systems that you are making. So, for example, at the moment, this paper was a theoretical paper that effectively we know would work. It's like the experiments have been done in so many other ways that we know if we just do the experiment, we find it. Actually, maybe there is an experiment in the paper. I need to remember. But all of these phenomena, they are highly dependent on the parameters of the system. So if you are doing it in a big photonic unit circuit, that's going to be a much different frequency to when you're doing it in the rods, which are much bigger. So effectively, if you wanted to engineer certain speeds of the switch itself, it would be dependent on how you've constructed your system. But it should be quick.
Can you go beyond the speed of the solid state transition?
I'm not so sure. I would need to think about that one. Yeah.
This is very fast actually. He's talking about intensity switching, not actually field switching, because it's very difficult to measure field. So finally we are measuring intensity. So of course field is fluctuating very fast in comparison to intensity, but we don't know how fast, because field is very difficult, it's attached with phase. So switching here is as a game, it's an intensity switching, but it's very fast. It's of the order of photon lifetime. That is power minus 12 seconds. So
Exactly. Yeah, exactly.
Yes, this is the useful case of optical logic for quantum computing.
And that's the nice thing about these systems, is there are many ways that these can be integrated on chip into the photonic circuit. The limitations come with the polarization symmetry breaking, because the technical side of it, the PICs are not polarization degenerate, but everything with the counter-propagating light, that is very easily realizable on chip. And actually, I don't know if the paper has been published yet, but there is a paper which shows the symmetry breaking happening on chip in silicon nitride.
So the key message, all this is flip-flop or gate or actually. So I always say that don't measure it, because do your experiment and do your everything before measurement, because once you measure it, it's slow. You are actually competing in two worlds. Optics is very fast world, electronics is very slow world. So if you attach these two worlds, so fast world is actually converted into slow world. So there is no meaning to attach these two worlds. So do your things in fast world, and finally when you reach the final point, detect it. So this is the way. This is NVIDIA is actually get rid of this point. This is the bottleneck of optical and electrical conversion. So if you get rid of this point before detection, then you actually speeding up the system. So optically it's very fast.
Yeah, there are many ways to utilize these different things. It's very nice.
Professor Nadu, I'm expecting something.
Oh, I'm just thinking about the Kerr, like, usually we can create an induced chirality in a system, like in the ring, with electric and magnetic fields, for example. So can you connect this to...
Yeah, so I mean, with many of these things, I made the point of having those assumptions of balanced inputs and things like this. But actually, there are many different types of phenomena which you can do when you introduce biases. So even things like birefringences in the system, they will typically favor one polarization or the other. And effectively, what happens then is that these nice connected effectively the connected nature of these bifurcation points, suddenly they split, so that now the ground to space, it has a defined preferred path. And so actually this can be quite useful because you can still enhance the differences between the different fields. And it's nothing to do with symmetry breaking because the symmetry is already broken. But you can still obtain many of the different types of sensors and things like this because there is still this exceptional point that is existing in the eigenspace.
So in terms of sensing.
Yeah.
So I think nobody has other questions. I have last question.
Yeah.
So at this point, it's an exceptional point, and when you study the two-coupled this nonlinear two-coupled oscillator system, so there are three terms: your symmetry breaking point, one is Hopf bifurcation point, and exceptional point.
Yeah.
What is the conceptual difference among these three?
So the Hopf bifurcation point is effectively when the field will start to oscillate. So I showed that the breathing solitons, these are solitons which are beyond the so-called Hopf bifurcation point, and that is why they do not stabilize. They are still with this oscillatory path. The symmetry breaking point is slightly similar because, as I mentioned, effectively this middle region, this middle region is unstable. So again, the system will start to oscillate just like with a Hopf, but because it is a solutions are available at that point, it will start to oscillate, but then it will find the stationary states, which are the symmetry broken states. Now, to complicate things further, actually, you can have a Hopf bifurcation of the asymmetric states, you can have Hopf bifurcation of the solitons, so all of these things, you can even have, I didn't show it today, but you can have multi-stability of the symmetry broken states. So really, the amount of manipulation that is possible using these different phenomena is vast.
So I'm just wondering about one more thing is that regarding the QRL. So as you have shown that you have the highly dynamical regime in sort of a state. So these dynamics actually can be used, can be generated as a QRL.
Yeah, and then the amount of randomness in the systems is...
I'm just wondering about the speed. What is the time scale of this?
Yeah, it is similar to the question earlier. It is very dependent upon which system you are using. So to give just generic numbers, I'm not sure I can, but it depends on the type of resonator, the materials that you are using, and also these, one thing I would say, these equations which are describing these systems. So effectively the variables that are involved, you have your input pump, which you can vary, you have your tuning, which you can vary, and to a lesser degree, actually you can vary this too and this one. And because these parameters are all coupled together, if you change your input pump, you can also change your tuning, and you can enter into vastly different ground spaces where the frequencies of different things are going to be very different. So actually it's a very programmable system as well, so you can actually vary the types. But the absolute limit of how quickly this randomness can be obtained, is dependent on the system.
One last question.
Yes.
Could you please just go back to the temporal soliton slide?
Yes. Which one?
The temporal inequality,
Yep.
with the equations.
Okay.
Where you wrote the nonlinear equations. So here, like when you make a change in the temporal soliton, you generate, in the amplitude of the field, you generate the soliton?
So there are a couple of different ways of generating solitons. So a soliton, you can inject a pulse of light, and then that pulse can evolve.
And due to nonlinearity, it would generate the soliton.
Yeah, exactly that. But I'll actually just dig out the old thesis a long time ago, because there are other ways of generating these solitons, actually using what's known as modulational instability. So that's actually utilizing the patterns by the Hopf bifurcation.
Because my question would be like how to like broke the symmetry while you are generating the solid.
Yeah. Okay. So here. So this is. So this is actually a different way of visualizing the fast time dynamics. Actually, this is very slick. So here along the x-axis, we actually have the fast time of the resonator. So this is the profile along our resonator. And so as we are varying the cavity tuning, first of all, we enter into a place where you have this modulational instability. So that means that there is a lot of randomness occurring in our system. First of all, it's symmetric. So this bottom panel is measuring the difference of the two fields. So where there's nothing, it's simply have symmetry. Then it turns at symmetry broken modulation instability, that's why it's around there. And then actually you can see the solitons naturally emerging in your system from the modulation instability.
Okay, so once the modulation and then broke the symmetry.
Yeah, so in this case, the symmetry is already broken below the threshold for solitons.
Okay.
So the MI has its symmetry broken, and then the solitons come afterwards. But equally, you can do the scan in the opposite direction. So you can scan forwards, and then here we have symmetric solitons. In this case, we've got two solitons. You can see that the difference between the profiles is nothing, so they're symmetric. But as we then scan backwards, we break the symmetry in the other way. We see that now there is asymmetry. So here, and actually you can see very obvious that this is a darker intensity soliton, which is bright, and this one is dark, and this one is bright. So you can also break the symmetry just moving backwards as well. But the generation, using the either pulse input or utilizing the MR.
How these formulation changes when you send this
Could you speak a bit louder? Sorry.
This is solitons actually, so the generation of solitons. So how would it change when it is the normal fiber and the photonics fiber?
That's a good question. It's very dependent upon the parameters. So basically all of these different thresholds, actually all of the topics throughout this presentation, the thresholds are very dependent upon the other experimental parameters in the system. So changing things like even the materials, the types of fibers, things like this, they will have very different influences. And there will be some types of components that will actually change things entirely. So there's something called cross-phase modulation, and if this gets too big, actually a very interesting phenomenon happens where the symmetry broken, we call it bubble, it opens, but it never closes, so there's never that restoration. So actually, using different materials or different parameter spaces, you can radically, like I say, it's such a diverse system which has so much controllability. To say how it affects it, I can't really answer because it's such a complex parameter space, but it should be possible.
I think there is no further questions. Thank you very much. Nice talk and informative talk. And may I request to everyone to have a group photo because I want to capture this moment. Switch on.